Welcome. In this session, we will talk about the basic rules of finding antiderivatives. Before I do that, I should point out this notation for the general antiderivative or the indefinite integral. This symbol is really an old-fashioned elongated S, and we will see the origin of this notation when we talk about, again, Riemann sums and definite integral in section 6. So we have these basic rules of integration, which we get by reversing the basic rules of differentiation. Differentiation distributes over addition and subtraction, and so does integration. An antiderivative of f plus g can be found by adding antiderivatives of f and of g. Same thing for subtraction. I can interchange differentiation and multiplication by a constant. So I can interchange integration and multiplication by a constant. We already saw an example of this when we found the antiderivative of x cubed last time. And then we have some rules for specific functions or specific types of functions. We know that the derivative of e power x is e power x, so the general antiderivative of e power x will be e power x plus c. Of course, the most basic rule of differentiation is the power rule. And by reversing that, we get the power rule for antiderivatives. The general antiderivative of x power n is x to the power n plus 1 over n plus 1 plus c. There is a caveat to this. This works only if n is not equal to negative 1. Because if n is equal to negative 1, n plus 1 is 0 and I cannot divide by 0. How do I prove this power rule? Basically the same approach we had for x cubed. To get x power n after I differentiate, I expect to have x to the power n plus 1 before I differentiate. If I differentiate x to the power n plus 1, I get n plus 1 times x power n. So I need to divide off the n plus 1, and that's where the denominator n plus 1 comes from in the antiderivative rule. Another way to think about the power rule is that we are doing the exact opposite of the power rule for differentiation. I can word the power rule for differentiation like this. Subtract 1 from the exponent, multiply by the old exponent. So opposite of subtracting 1 is adding 1. Opposite of old is new. And opposite of multiply is divide. So to find antiderivative of x power n, I add 1 to the exponent, then divide by the new exponent. Now what about the whole in this, the thing that we left out? The power rule works for any exponent, positive or negative or fraction or integer. It even works for irrational numbers as long as it's a constant, with one important exception. It does not work if the exponent is negative 1. In other words, power rule works for 1 over x squared. It doesn't work for 1 over x. Turns out the general antiderivative of 1 over x is ln of absolute value of x plus constant. Of course, we know that if I differentiate ln of x, I will get 1 over x. But we have to explain the absolute value, which we will do later. For now, let's just look at how we can use the power rule for other constant exponents. So to find an antiderivative or the general antiderivative of the function in our next example, x power 4 plus 3 square root of x plus 2 over x cubed minus 5 over cube root of x power 4, I start by writing each term as a number times a constant power of x. So the first term is of course x power 4. The second term I have plus 3 square root of x. Square root of x is x power 1 half. In the third term, I have 2 over x cubed. It's 2x to the power negative 3. The exponent is negative because I'm bringing it to the numerator from the denominator. In the last term, the coefficient is negative 5. I have a cube root. Let's divide the exponent by 3. The denominator is x to the power 4 thirds. I want to bring it to the numerator, so I should change the sign of the exponent, which makes it x to the power negative 4 thirds. Now I can apply the power rule, and just this time I will write it out in detail. For every constant power of x, in this case in every term, you add 1 to the exponent, then you divide by the new exponent. This is a particular antiderivative. To get the general antiderivative, I add a plus c. The rest of it is really just arithmetic. I am going to simplify by doing the addition in all the exponents and all the denominators. So the first term is x power 5 over 5. Second term I have 3 times x to the power 3 halves over 3 halves. 3 divided by 3 halves is 3 times 2/3 or 2. So I can simplify this further. But for now, let's just do the arithmetic. The third term I have 2x power negative 2 over negative 2. In the last term I have negative 5x to the power negative 1/3 over negative 1/3. And if I do the arithmetic in the coefficients, 3 divided by 3 halves is 2. 2 divided by negative 2 is negative 1. Negative 5 divided by negative 1/3 is 15, so which gives me the answer. There are two important points to note here. One is that even though we distributed the integral over all the terms, we just need one constant of integration. There is no need to put a separate constant of integration for each term. Even if we did, we can combine all of those into a single constant term. This leads to a confusing thing. I will try to avoid the confusion by using appropriate notation. But the plus c doesn't stand for a specific number c, but stands for a generic number. So it's like a pronoun, and like all pronouns, it can be confusing when you use the same pronoun to talk about different things. So it's like saying he when there are 2 or 3 people you are talking about and you don't know who the he refers to. Sometimes it matters, sometimes it doesn't. And in integration, usually it doesn't matter what the plus c refers to, as long as you remember that it doesn't necessarily refer to a specific number we don't know. The second point is much more important. When you differentiate, the form of the function usually doesn't matter. For example, I can differentiate 1 over x cubed by using the quotient rule, leaving it as a fraction. Or I can write it as a negative exponent, x power negative 3, and apply the power rule. The difference is simply a matter of convenience, not of absolute possibility. This is not true of integration. There is no product rule, there is no quotient rule for integration. If you write it as 1 over x cubed, you cannot do the integration. You have to write it as x power negative 3. So in integration, the form of the function matters. And for power rule, it has to be a constant power in the numerator. It cannot be in the denominator. So if you're one of those people, a couple of those still in this class, who differentiate things like 1 over x cubed by using the quotient rule, you have to change your ways. You cannot integrate 1 over x cubed by using anything like a quotient rule. You have to write it as x power negative 3. We will talk about variations of this next time, as well as the other rules of integration in later sessions.